All right, so next up in our kind of quest or exploration of looking at a whole bunch of different examples of this mathematical induction is going to be an example that looks into this world of division, or in this case, we're going to be asking whether or not something is going to divide something else. So in this case, the statement's going to read, you're going to give me some non-negative integer. I'm going to refer to that thing as an n, and I'm going to claim that 6 is going to divide n cubed minus n. So in this case, I have this statement about division, and if you go back to some of the earlier notes that we had about this notion of divides, we know that this connects nicely into this world of modular arithmetic. That is, I know this question of does 6 divide n cubed minus n is going to be the exact same question as whether or not n cubed minus n is actually going to be congruent to 0 in this mod 6 world. So I'm actually going to be working with this right expression. I actually think it's a little bit easier to work with this notion of modular arithmetic. We have this really nice algebra underlying all of it, so it's easy to move things about. So when I have my kind of declarative kind of induction hypothesis, I know that I can just write it as something like this, and then it's a little bit easier to move around. I don't have to worry about extra variables coming into play and all of that kind of gross stuff. So in this case, we're going to be working with this expression over here. I'm going to try to think about a few examples just to see if I know what's going on, so I actually believe that this thing might be true. So in this case, if I pick my first favorite non-negative integer, I'm going to say, okay, what happens when n is going to be 0? Which we know when we jump into the actual proof, this is actually going to become my basis step. So it's not actually kind of wasted effort by looking at this 0 case. It's going to first tell me that I kind of believe what's going on a little bit, as well as becoming that first basis step. So in this case, if I plug n being 0 into this expression that I have boxed, I'm going to see something of the form, well, a 0 cubed minus a 0. I know that that's going to be a 0, and 0 is most certainly going to be a 0 in this mod 6 setting. So yay, that seems to work out, at least in this case. Okay, let's jump up one little step, I guess. Let's look at when n is going to be a 1. Well, if I look at 1 cubed minus 1, I know that that's going to be a 1 minus 1, which is a 0. And hey, 0 I know is going to be a congruent to 0 mod 6, so I'm good in that case as well. What happens when I jump up to a 2? Well, if I look at a 2 cubed minus a 2, I know that this is going to kick out something like an 8 minus a 2, which is a 6, and I know that 6 is actually congruent to 0 in this mod 6 setting. So it seems to be at least believable for the first few things. If I actually jump this into a line of Sage code, I can help my computation out just a little bit. So in this case, what's going to happen is I'm just going to run through the first 20 integers, so going from 0 up to 20. I'm going to print out that value n. I'm going to print out that n cubed minus n, and then I'm also going to print out what that thing is reduced in this mod 6 setting. So in this case, you can see, well, when n is 0, I have the 0. When n was a 1, I got a 0. When n was 2, I got the 6 that I just saw. So hey, I can actually do some cubing, so that's good. And I know that 6 reduces to a 0. I have that if I were to plug in a 3 into that expression, I'd have a 3 cubed minus a 3, which is going to be my 27 minus a 3, which is a 24. And I know that 24 is divisible by 6, so it reduces down to a 0. And as you go down this whole tree, you see all of these zeros popping out over and over and over again. But we know that that's not necessarily good enough. This is only going up to 20. I have to think about pushing this thing all of the way to as large as I'd ever want to, and then keep on going. So that's where this question about induction is going to come into play. This thing is set up very nicely. If you look at this overall expression, it is already in that nice form. It's going to read something of the form, for all n's in this world of non-negative numbers, I'm going to have some predicate emerge afterwards. So in this case, my Pn is going to be this expression that's going to say, well, exactly what I'm looking at. This question that n cubed minus n is going to be 0 in this mod 6 setting. So now I got everything set up nicely to actually look into the induction side of things. So that's what I'm going to do on this next slide. So in this case, I'm reiterating what this Pn is going to be. It's this expression that says n cubed minus n is 0 mod 6. The basis step is going to be, well, what happens when I stuff 0 into this thing? Well, we know if I plug 0 into this thing, I'm going to get a 0 cubed minus a 0, and we already saw that that's a 0, and 0 is most certainly 0 in this mod 6 setting. So yay. Like I said, the basis step is usually pretty easy to look at. You just got to kind of do that one operator and see what happens afterwards. So here's where things get a little bit more dicey. I now have to dive into this inductive step. So here's where I get to assume pk is true. Let me actually make that a red. So pk in this case is going to say that k squared, k cubed I should say, k cubed minus k is going to be 0 mod 6. So in this case, I'm at the kth rung of this ladder, and I want to go up one extra step. So what I want to show, and I'll do this in green, I want to show that p of k plus 1 is true. So my goal in this case is to get to the stage that k plus 1 quantity cubed minus a k plus 1 is going to be a 0 in this mod 6 setting. So that's my goal, is to show that thing in green. And this is actually a pretty nice inductive result because you actually have a little bit of guidance. What I'm going to do is I'm going to start with that left-hand side of that thing, expand it out, and hope to see that I can get a whole bunch of things reduced down to a 0. So in this case, what's going to happen is I'm going to look at k plus 1 cubed minus a k plus 1. What I have to do in this case, I have to take this k plus 1 and I have to cube it out. So what's going to happen is you're going to have something like a k plus 1 multiplied by a k plus 1 multiplied by a k plus 1. And if you multiply all of that stuff out, what's going to happen is you're going to get a k cubed plus a 3k squared plus a 3k plus a 1. If you want to actually do the full foiling on that and then do that double distribution on that extra k plus 1, you will in fact see that expression kick out. Okay, so what happens when I actually bring that thing back up? You're going to see some really nice things actually occur. I'm going to have a k cubed plus a 3k squared plus a 3k plus a 1, and then I'm going to subtract off, in this case, I'm going to distribute that negative sign here as well, subtracting off a k and subtracting off a 1. So let me get rid of that computation down here so I have a little bit of room to work with. So now you're going to look at this thing and be like, all right, well, what's going on at this expression? Do I have good things occurring here? Do I have bad things occurring here? What do I want to see actually come into play? Okay, so what I'm going to do right away is I'm actually going to kill off those little ones. So in this case, that plus 1 and that negative 1, those add up to a 0, and that's great. The thing that's somewhat trickier, what you'd want to do, because this goes back to your algebra days, you see this little 3k and you see that little negative k. You might be tempted to actually combine those two things together to become a 2k. In this case, you don't want to do that. And the reason why you don't want to do that is you want to see something like a k cubed minus a k emerge, because I know when I reduce that thing mod 6, that's going to turn into a 0. So if I can see a k cubed with a minus k, I know that those two things together are going to turn into a 0. So in this case, I'm going to write those things next to each other. I'm going to have that k cubed, there's going to be that minus k, and I know that that's going to turn into a 0 once I do this reduction modulo 6. So what I'm left with then is a few extra terms. I have this 3k squared and a 3k, and if I factor that thing, I'm going to write that as a 3 times a k multiplied by a k plus 1. So here's where things get a little bit more interesting. We know that when we reduce this thing modulo 6, this is going to kick out a 0. Because of my induction hypothesis. This is using this big fact up here, so I know that that's actually going to turn into a 0 mod 6. The question is does this part right here turn into a 0 mod 6? Well, if you think about what does it mean for something to reduce down to a 0 mod 6, well, you're going to have some multiple of 6 existing somewhere. Well, in this case, you have a 3, and you know that 6 is equal to 3 times 2, so you're almost there. All you need is that this little expression right here is going to turn into an even number. If this 3 is multiplied by an even number, I know that that entire expression is going to be a multiple of 6. That is, when I reduce this thing by 6, it's going to turn into a 0. So if you look at these two numbers of k and k plus 1, the really, really special thing to notice at that stage is that those two numbers are actually going to be consecutive. So I'm going to have k followed by a k plus 1. So in this case, you have kind of two different cases to think about. Well, if k is actually an even number to start with, well then there's my even number. There's an even number here multiplied by a 3. There's a 6 hiding in there, and everything is great. If k happened to be an odd number, well then the number after it is going to be an even number. So then, hey, the k plus 1 is going to be my even number, and you multiply that thing by a 3, and there's that 6, and everything is great. The idea is that k and k plus 1 are consecutive, so one of those two numbers has to be divisible by 2. That is, one of those two numbers has to be even. So in this case, either k or k plus 1 is the even number. I don't really care which one it is. I know it's at least one of them. So I have an even number here multiplied by a 3 is going to tell me that that whole expression is going to be a 0 in this mod 6 setting. So in this case, I have a 0 here, I have a 0 here, which is to say that that entire expression is actually going to kick out a 0 modulo 6, which is exactly what I wanted to show. So in this case, I do have that my inductive step is is satisfied, so everything is good. What I'm going to do next is just kind of quickly run through the slightly cleaned up version of this proof so you can see all of the little pieces coming into play. The first thing is just a really quick remark that the original thing was talking about this notion of divides. I could actually convert this thing into this question of whether or not I'm congruent to 0 mod 6. If I really wanted to, I could move that n over and actually look at this expression that says n cubed is congruent to n mod 6. I think it's easiest to look at things being set equal to 0 because it's easy to look for zeros rather than trying to look for little n's randomly throughout everything. Okay, so in this case, what's going to happen is that when I start that proof, I'm going to tell you right away what my predicate, this Pn, is going to be. So in this case, I'm going to let Pn be this expression that says n cubed minus n is a 0 mod 6. So that's the thing that we've been working with over and over and over again. The basis step is to simply say this thing is true if I plug 0 into it. So if you plug in 0 into that left-hand side, everything turns into a 0, and I know that 0 is congruent to 0, so everything is great. So that's going to say P of 0 is true. So that tells me, hey, I'm on the ladder, that's great. What I want to do next is I want to tell you how to climb from rung to rung. So in this case, my inductive step is going to say I get to assume pk is true, and I have to show pk plus 1 is true. So in this case, I get to assume pk, which becomes this fact that k cubed minus k is going to be 0 mod 6, and my goal is to show pk plus 1 is true. So that's the component that I wrote in green on that previous slide. So I have my bit in red, I have this bit in green that I'm trying to work for. So this idea is I'm going to expand out that left-hand side. I officially said expanding k plus 1 cubed, which is going to kick out that expression. I'm still subtracting off my k plus 1. Here's where I killed off those little 1's and then did that little sneaky step of bringing that k cubed with that minus k. Like I said, students a lot of times when they're working with these things are very tempted to combine that with the 3k because that's what you've been trained to do for years and years and years is you see a 3k, you see a minus k, combine those to become a 2k. But in this case, I do want to see that k cubed minus k. That k cubed minus k is right there, and I know that that's going to turn into a 0 when I do this reduction mod 6. So in this case, here's where I'm going to say, oh, I have this little 3 multiplied by 2 things. One of those things must be even, which gives me that k multiplied by k plus 1 is even. That gives me that that big expression is going to be this nice multiple of 6, which is going to say when I reduce this thing modulo 6, it is as well going to turn into a 0. So at the end of the day, that's a 0, that's a 0. The whole entire expression must be a 0. Therefore, I've actually satisfied this inductive step, this idea that if I assume pk is true, I can climb up to the next rung of the ladder, and I'm done at that stage. So those two components combine to create this nice mathematical inductive proof, and everything is great after that. If you are interested, just as kind of a quick kind of coming back on some of the direct proofs, you could actually go back and redo this proof without using induction. So in this case, what ends up happening is that if you look at this expression n cubed minus n, it actually does factor completely right away from the beginning. So in this case, if you actually factor n cubed minus n, it becomes an n minus 1 multiplied by an n, and then multiplied by another n plus 1. So in this case, what ends up happening is I have the product of 3 consecutive numbers. The idea is that one of those numbers must be divisible by 3, and one of those numbers must be divisible by 2. We actually have this little fact that says if you give me 5 consecutive numbers, then at least one of them must be divisible by 5. If you give me 17 consecutive numbers, one of them must be divisible by 17. In general, if you give me k consecutive integers, at least one of them is divisible by k. So in this case, that's exactly kind of a generalization of this even-odd parity question. If you give me 2 numbers, at least one of them must be even, which is to say one of them must be divisible by 2. So like I said, you could actually go back to this result that we had in the beginning, attack it with a direct proof, but I actually think it's a little bit easier to go at it with this inductive proof. You don't have to go into this really kind of strange factoring question. You get that immediately from the beginning. But if you're interested, you can kind of explore that result a little bit quicker, kind of just pause it, see if you can read through that proof and make a little bit of sense out of it. It was more kind of just a, hey, by chance, this actually kind of comes into play. This really shows that underlying structure about what's going on. But what I wanted to see is that you could actually attack this thing with this inductive idea.